Okay, off we go. So last time we just finished this example, one of several examples that we saw about how to use these, I think, extremely powerful theorems called symmetry theorems, right? And to be fair, I'm only showing you really kind of one symmetry theorem, that is the odd symmetry theorem, and we talked about the particulars of that theorem. So let's see another example. This is a sort of an anti-example. This is a landmine. This is the kind of question where a lot of students will take a nasty hit. And I think it's good to see those in advance so you don't accidentally step on that landmine. So we have here a triangle T, and it has given corners, and you can draw a picture of that pretty readily. Let's see here. The corners are at here and there, and so our domain looks like this. And oh my gosh, look at that. There's a symmetry over the y-axis. Oh my gosh, look at our integrand. It's an odd power. Integrand is odd. Domain is symmetric. Integral 0 by symmetry. So it would seem. So a lot of students would write down on their paper and turn the page and move along, confident they've gotten it right, and nothing they have written represents progress toward an actual solution because the domain is symmetric over the y-axis, right? But if you think about it, reflection over the y-axis puts a minus sign on the x-coordinate. This does not negate when you put a minus sign on the x-coordinate. It negates when you put a minus sign on the y-coordinate. In other words, if you were reflecting through the x-axis, then that would be odd. Right? So we have a symmetric domain, yes, but the line of symmetry for the domain and the line of odd symmetry for the integrand are different lines. The symmetry theorem does not apply. Does everybody see why the symmetry theorem doesn't apply here? Right? And does everybody see why there's this temptation to try to invoke it? Any question? I mean, feel free. Again, dangerous scenario. You want to make sure that you don't fall into this little trap. Which, by the way, I mean, let me point out, I don't like setting traps for students, right? I'm not trying to be, to be a bad guy. But my point is that comes up naturally. This kind of thing comes up naturally all the time, right? And so you have to be on the lookout for this because otherwise, I could be long, out of your life and this kind of thing will happen. All right. So last thing we'll say about symmetry, and then we'll move on, is three-dimensional symmetry arguments. And good news, it's exactly what you would expect. We have a three-dimensional notion of reflection. This is the notion of reflection that you see every time you look in a mirror. Right? It's arguably the most sort of relatable version of a reflection, is reflecting through a plane. And we can then write down the same basic ideas of what does it mean for a function to be odd, and that is that when you reflect the input, you negate the output. Right? What does it mean for a domain to be symmetric? Well, it is its own reflection. Various different ways you can say the same thing there. We get the exact same theorem. Right? If you have an odd integrand over a symmetric domain, then your integral is 0. Totally awesome. Same two warnings. You do need both conditions, and you've got to use the same plane for both. So, same exact story, just three-dimensional instead of two. Okay, let's see an example of this. This is actually a really nice example. Look at this integral here. And let's contemplate how we would do this without a symmetry argument. And the old-fashioned way to do this would be to slice up your unit ball in rectangular coordinates, square roots everywhere, nightmares, right? Horror story. We're not going to even toy with that. That would be an outrage. Hey, maybe we do this in spherical coordinates. You could do this in spherical coordinates. X, Y, and Z, each of them are full of trig, which means this integrand is going to be a massive inconvenience of trig. Don't forget your stretching factor, which has more trig. This would be a really, really inconvenient trig exercise. Right? So don't really want to have to do that either, although it's the better of the two options. Okay, so here's the argument I am going to make, and that is, let's think about symmetry through the XY plane. Right, the XY plane like this. Reflecting through the XY plane will negate the Z coordinate. Right, so that's why we have this minus sign here. Is that cool? Everybody with me? Conveniently, unit balls are symmetric through, well, any plane containing the origin, so that's nice and convenient. And the question now is the integrand odd? And why, yes, it is. And the short version of why the integrand is odd, I mean, you write down the algebra, but if you're doing this kind of in your head, again, you don't have to write down the algebra. The algebra here is so you can feel confident about what you're claiming, right? I look at this integrand and I think, look, the odd power is on the Z. The reflection negates the Z. Getting a minus sign on that Z will get cubed, which stays as a minus sign. And so, this is an odd integrand, and odd integrand symmetric domain. Boom. Disappears in a puff of smoke, integral 0 by symmetry. Everybody happy with that? Very cool argument. Yeah?
Right, but doesn't just have the previous one, the triangle one?
The triangle one? Oh, this one here?
Yeah.
So what part?
If you negate the y cube, wouldn't you end up having?
Yeah.
The f of the reflection wouldn't be negative f.
The problem is that negating the y would require us to reflect over the x-axis. But to have symmetry of the domain, we'd have to reflect over the y-axis. And so the problem is two different lines.
Mm-hmm.
In other words, there is no symmetry argument. Yeah. Exactly. Okay, let me say I'm going to give you a different point of view on this example. Let's suppose that I did not know that I should use the XY plane. And therefore I did not know that was going to be my formula for reflection. Right? So take that away. Now, how do I solve this problem? And what I would do is I would say, look, this domain, it's the unit ball. I've got a bazillion options for planes. I mean, this ball is going to pick any plane containing the origin. The unit ball is going to be symmetric. So let's not even worry about that yet. Let's think about our integrand. I would like for this to be odd. What would I have to have in order to make this be odd? And then you can look at these exponents. You see that this one is an odd exponent. And I think, hey, I sure wish my reflection formula just negated the Z. I can kind of do this algebra, just count the minus signs. I would like to negate the Z. So I'm going to say this formula motivates that I want this formula for my reflection. Everybody say that's a kind of a strategic reverse engineering, right? Once I see, I wish that was my formula for reflection, then I have to ask, well, is that a reflection? And if this is a reflection, what is it a reflection through? And you think about the picture, and well, that is a reflection through the XY plane, right? So when I was writing this example, I wrote the Z cubed, and then I thought to myself, hey, I want the minus sign to be on the Z. Oh, I guess that means I need this to be the XY plane.
So yes. If all the variables are have even exponents, there are no reflections.
Then yeah, that's right. And not only would we not have a symmetry argument, there couldn't be at least an odd symmetry argument because the integrand's always positive, right? And symmetry arguments ultimately are all about cancellations. You need to have some positive, some negative. So if these were all even powers, it'd be not possible to have totally. All right. Okay, so that's sometimes this is a useful trick for figuring out what plane of symmetry you should be using. Okay, so that's chapter 5. We're going to move along to chapter... excuse me, I'm sorry, I got ahead of myself. That's 5.5. Now we move on to 5.6. Okay, applications. There are, tough choices and all of that. I'm going to move kind of quickly through this stuff. Ultimately, these are just some kind of clever ideas of how you can apply some of the tools we've created. So I'm going to start with this idea of averaging. Well, y'all know how to average, and we don't need to talk about that. That's pretty boring. And of course, you see I did some arithmetic here. The arithmetic is kind of trivial. But notice if you rewrite it like this, I can reinterpret what we're doing. Right? If you look at on the left here, I'm averaging 6 numbers, which I do by adding them up and dividing by 6. Okay, well, yeah, but, I mean, look, it's really kind of 3 numbers. There's 4, 7, and 8. Those are the numbers. I'm just counting 4 twice. I'm double counting the 4, and I'm triple counting the 8. So I'm going to say, even though this was just arithmetic, I mean, in some sense, nothing happened, right? The 2s there and there are accounting for the fact that we're double counting the 4. And the 3s here and here are accounting for the fact that we're triple counting the 8. Is that cool? Does everybody kind of see what I'm talking about? Okay. All right, so this is called a weighted average. We're averaging 3 numbers, 4, 7, and 8. I'm just double counting the 2, or you might say I'm counting that 4 with weight 2, and I'm counting the 8 with weight 3. And this formula generalizes very naturally. It's exactly what you would think. Notice that's the kind of general structure, and these weights, these weights here, they show up as structurally kind of in the same places in the general formula. Does that seem reasonable? Okay, cool. A fun example, kind of a twofer example here is how we do grades in this course. And y'all, I hope, will recall from the start of the semester, every graded item in this course will be on the sort of the 4-point scale. So 4.0 means A and 3.7 means A minus, like that. And you'll have a bunch of grades on a bunch of graded items, and we will do a weighted average exactly per this formula, right? Weighted average. And specifically, there are certain weights that are advertised. Now here, in this hypothetical example, the weights are these numbers. Now in our class, they're a little bit different, and it's a good thing we write these things down. Anyway, the weights are a little bit different from this. Right? Something has 7% weight and something has 3% weight. It's all written down on the websites. Anyway, how do we do a weighted average given some weights, given some grades that we need to do weighted average of? Well, we follow the formula. Here's the formula for the weighted average, which plays out like this. And notice the grades, the things that we're doing weighted averages of, go where those go. And then let's see, the weights go here and here. It's just following the formula, right? Weighted average. And for Bob, it works out like so, and that's just under 3.0, so we round it up, and Bob gets a B. Everybody see how that arithmetic works? It's very straightforward arithmetic. And by the way, I encourage you all to use this formula to take, very soon. We have an exam 2's coming up in the end of this week, right? And we should probably start writing that exam. I haven't even started yet. But so y'all will have grades for exam 1 and exam 2 pretty soon, and you can speculate about your attendance grade and your homework grade if that's all going along well. half of your grade will be determined pretty soon, right? And then you can look at the other half and you can say, all right, well, what grades will I have to get? If I get such and such on the third exam, what will I have to get on the final? And you can just go through and do arithmetic, solve for whatever it is that you want to know, right? And some simple high school algebra will allow you to see, what kind of a position you're in and what will you have to get on the final in order to bring your grade up to whatever grade, whatever, right? So I think those are useful calculations, and this is formulas you'll work with. Lastly, I'll mention if you're not comfortable with, what any of this stuff means relating to course grades in this class, please do come talk to me. I want to make sure everybody is very, very clear on how the grades formula works in this class. So just come talk to me. I'll be happy to, write down some scenarios and make sure everybody understands. Okay. So, the formula we've written down so far only works for a finite number of numbers. Right here we have a finite summation. Right, if you're averaging a finite number of things, what if you're averaging an infinite number of things? And in particular, if you want to know the average value of a function, notice that's an infinite number of different values, because between A and B there are infinitely many different inputs, therefore infinitely many different outputs to average. And the way we deal with this is we pretty much copy that formula with a little asterisk that we use size in the domain is what we use as the weights. So dx being size in the domain, that serves as our weights. So it's a pretty natural formula to write down. This is our formula for the average value of a function. Some of you may have seen in your high school calculus courses a different point of view on the average value of a function, and you can persuade yourself that this is the value that if we were to look at that single value instead of whatever the function is, the area under the graph of f is the same as the area of the rectangle that has this height. Right, so it's a different take, same formula. All right. Then I'm just going to point out that there's no particular reason that this had to be a one-dimensional domain. We can still talk about size in the domain being the weights, even in a more general case of a multivariable function. So for two-dimensional domain, here is the same general structure, and area now is what we mean by size in the domain. So this formula here still is just using size in the domain as weights and writing down a weighted average. Okay, so again, plug and chug on this example. It's a good little exercise. It's a pretty straight read, so I encourage you to take a look at that. Okay, a little physics. There's an idea of this thing called center of mass. You can motivate center of mass in different ways. It has a lot of useful features, and this is not a physics class, so I'm going to do very little of that. But here's a pithy little point of view, sort of a math point of view on why we would care about center of mass. It is a weighted average of position. Not very physicsy, but it's pretty natural extension of what we've been talking about. So here it is, weighted average. We're literally using the weights themselves, or let's say the masses themselves as our weights, and you can see them right there in the formula. And we're doing a weighted average of position. You can see the position values, these x coordinates. Right there in the formula. So, weighted average of position. And what do you do with this? Like, why would I ever care about such a thing? That's where you would put your finger if you had these masses connected, some sort of a rigid structure, X bar is where you would put your finger to make this balance. It's the balance position. So it's physically pretty natural. How are we doing? Is everybody okay? By the way, this is a good exercise. If you're interested, again, you don't have to, but it's instructive, to look at, if you had your finger there, and then think about this distance and that mass and that corresponding force, and think about the counterclockwise torque that M1 would create. And then you think about this distance and that larger, perhaps, mass and the amount of torque, clockwise torque, that M2 would create, and note that they will balance perfectly. Same amount of torque in opposite directions. So easy little bit of algebra, and take you a couple of minutes. Works out nicely. Okay, we can generalize this. If you have not two pieces of mass, but if you have more pieces of mass distributed over regions. Again, kind of copying the same sort of a structure. And again, notice we're using the masses as the weights and the weighted average. Okay. Excuse me. So here's the weird thing. The weird thing is, in this formula that we have here, notice that integral. That integral has an integrand. The integrand is a vector. That's a little weird. We've never seen an integrand that was a vector before, right? I kind of hope this did creep you out a little bit. You should have a natural discomfort with writing things down that we haven't defined, right? So it is a little uncomfortable. What do we mean by this? What is an integral of a vector-valued integrand? And it turns out it actually makes loads of sense. After all, how do you multiply a vector times a scalar? One coordinate at a time. How do you then add up a bunch of resulting vectors? One coordinate at a time. And so this whole construction, we compute one coordinate at a time. So we're going to compute overall the location of the center of mass by first computing its first coordinate as a weighted average of the first coordinates, and the second coordinate as a weighted average of the second coordinates, etc. So one coordinate at a time. Okay. All right, example. Let's see here. We are looking at this upper half disk. I'm going to say that the mass is distributed in that upper half disk in a nice uniform way, constant density, density 1. Just to keep it, first example, easy. That, of course, in general could be anything, who knows what. And let's see here. How would we compute these, the coordinates of the center of mass? And, well, here's the x coordinate, here's the y coordinate. Notice each one is just a weighted average of the corresponding coordinates. And then you compute. Okay, so a couple of nice lessons in how this has worked out. The first is, notice, when we write down this formula, this first formula up here, x bar, write this down, there was no indication in the statement of the question that symmetry would be useful. Hint, hint, think about using symmetry. Life doesn't do that to us, sadly, right? So we have to be kind of constantly head on a swivel looking for these opportunities to use awesome computational tools like symmetry arguments, right? So there are some details to be thought through. Make sure you are good with those details. And in particular, one of those details is that we make our symmetry argument over the y-axis. You want to think it through. Make sure that not only do you see that the domain is symmetric, but recall that you also need for the integrand to have odd symmetry when we reflect over that same axis. Is that cool? All right, here's another nice lesson from same example. And that is, this integral right here is one of the landmine examples that I was warning y'all about earlier. This is totally a landmine example. Because if you weren't thinking too carefully, you would notice, okay, my domain is symmetric. And check it out, my integrand has an odd exponent. Sweet. Right? If you're moving a little too fast, a little too loose, you will see a symmetric domain and an odd, seemingly, casual glance, seemingly an odd integrand. You will declare this to be zero by symmetry. And it's not a true conclusion. The argument doesn't exist. There is no progress toward an actual computation there. And look how easy it is to step on that landmine. Does everybody see what I'm talking about here? I mean, this is not a contrived situation. Look how natural this is. Just a half disk. We just want to find where the center of mass is. That's where that integral came from. I did not craft that. That's very natural. So watch out, please. I don't want anybody stepping on these kinds of landmines. Okay, last thing I'll point out, and this is just kind of an aside, but this integral, if you sort of write it down, there's the constant out front, of course, who cares? But if you look at your options on which way to slice, do you do this dy dx? Do you do this dx dy? Either way, we don't hit any corners. So that's kind of a push. Either way, I am going to have to solve for either x as a function of y or y as a function of x. Either way, I'm going to be dealing with the fact that that circle is going to create square roots. So both of my outer integrals, both have integrands that it would seem are going to have square roots in them. So these are our two primary criteria from chapter 5 to decide, well, wait a second, which way should I do dx dy or dy dx? Try not to slice through corners. Try to avoid creating square roots in your inner bounds. Neither one of those criteria particularly suggests one of these over the other, right? So from a chapter 5 point of view, or from a 5.2 point of view, it's not clear which one of these is going to be better. So check this out, though. Very first thing you would do down here is do the y antiderivative of y. That gives you 1/2 y squared. The square root gets plugged into a square. The square root disappears, and life is good. Right? So I think the second integral, take your pick, right? But the second integral is going to be a lot easier. So sometimes you can see this coming, right? Sometimes when you're trying to decide which way to go, if you know what your integrand is, you can think in terms of, all right, well, would I rather take a y antiderivative first, or would I rather take an x antiderivative first? And since there's this threat of square roots, before I even do any real work, I can see I like the idea of doing my y antiderivative first. Let's get a square to defend myself against the square roots. So something to think about. It's kind of a secondary, criterion, secondary consideration. Sometimes useful. Okay. All right. Okay, moment of inertia, neat physics idea. This isn't a physics class, so I'm not going to spend too terribly much time on this. The big idea, though, is that if you have an axis and if you have a piece of mass, and if that piece of mass is rotating around the axis, and you want to talk about kinetic energy, no problem. Kinetic energy, 1/2 mv squared, old news. Here's where that formula doesn't work very, very well. And that is if my mass is a much larger, not a point mass, but a lump. Something like that. And let's suppose that's rotating around the axis. And I want to compute the kinetic energy. Can I use this formula, 1/2 mv squared? And I claim we can't really, because a little piece of mass, let's say that's not what I want. wanted. Little piece of mass, let's say about right there. It's moving with a certain speed. But a little piece of mass way out here, much farther from the axis, traveling a much greater distance in the same amount of time, is literally moving faster. It has a greater speed. Which of these speeds do I use for my V in that formula? And the answer is, it doesn't work that way, and this, we just can't do it like this. Right? Is that cool? Okay. So what do we do about this? And I wish I had time to go through this derivation. It's just some details. If you're interested, come talk to me. I'd be very happy. The office hours or whatever after class. It is pretty cool. But here's the punchline. The punchline is that the kinetic energy, let me get back into highlighter mode. The kinetic energy that we previously computed with 1/2 mv squared is instead computed with this crazy formula, which doesn't look particularly similar. Until you notice that this thing right here, if I were to rename that as a single thing, we're going to call it moment of inertia. Now, notice, first of all, this thing called moment of inertia is intrinsic to the mass. It doesn't matter. This does not make any reference to how the mass is moving, just what's the mass and how far is each piece of mass away from the axis. This is intrinsic to how the mass sits in relation to the axis. The actual, how fast is it going around, this is what we call angular speed, is independent of that. And when you write it like that, and then you compare our old, that's not the color I wanted. You compare our old formula for kinetic energy to our new formula for kinetic energy. You see they're pretty analogous. Structurally, they're kind of the same. 1/2 something times something squared. And furthermore, check out how analogous these things are. V is our speed. This is the rate of change of your linear coordinates with respect to time. Omega is your angular speed. That's your rate of change of your angular coordinate with respect to time. Literally, omega is an angular analog of speed. So these formulas are starting to look an awful lot alike. They have the same structure, and linear speed gets replaced by angular speed. And the half is in both of them as well, of course. And that kind of suggests, though, that a reasonable interpretation of I is that it's kind of an angular analog of mass. It's playing the role that mass played in this equation. Everybody kind of see what I'm talking about there? And again, we don't have time to do all the physics derivation. Cool though it is. So this is the takeaway. This is the way I'd like for y'all to think about moment of inertia. I gotta hit better. Moment of inertia, computed with this formula, represented typically with I, it plays a role kind of analogous to mass when you're talking about kinetic energy from an angular standpoint. Okay, that's the intuition for it. Okay, so let's talk about how to compute this. Make sure to memorize this formula, integral r squared dm. The integral is appropriate to what your domain is. If we have a 3-dimensional solid, then it's a triple integral. If you have a 2-dimensional distribution of mass, then it's a double integral. Right? Whatever integral kind of makes sense. dm is density times size. Size is either dv for a triple integral, dA for a double integral. It's exactly what you would think. And the only little tricky bit is what is r. And I am sorry to report that when you look at it in the formula, you might think, oh, that's a cylindrical coordinate, right? That's distance from the z-axis, and it's not. That r, you see up here from the picture, that r represents the distance from whichever little piece of mass you're talking about to the axis of rotation, whatever axis you're rotating around. There is no reasonable assumption that you're rotating around the z-axis. Right? So it's unfortunate that we call this r. It's kind of a confusing choice. And unfortunately, this is pretty standard, and so y'all just going to have to remember that in the formula for moment of inertia, this is not the usual r. It represents distance from whichever piece of mass you're looking at to the axis that it's rotating around. So, for example, if you're rotating around, well, if you are rotating around the z-axis, then that distance is good old cylindrical r. That's nice. Sometimes you get lucky. But if you are rotating around that axis, parallel to the x-axis, for a couple of different given values of y and z. Totally different axis. And distance to that line is computed by a different formula. And you gotta think it through every time. Right? Now, for whatever it's worth, some students like to memorize a short list of cases. I think it's a mistake. Whatever you memorize right before the test, you will not remember. Certainly not 15 years from now when you're mid-career, right? So it's just kind of a bad plan, I think, overall. I think what you should do, let me rephrase, what I have done, right, how I've gone through my math and physics experiences is understand the concept, its distance from wherever you're looking at to the axis in question, and let geometry answer the question for you every time you need it. So, for example, let's look at this example here. Here's our region. And let's see here. Mass is distributed, you'll notice, in a non-constant way, right? So the mass is not distributed the same everywhere. It's more dense kind of on the sides and less dense in the middle. Okay, well, if we were rotating around the x-axis, and you could imagine, perhaps this thing is rotating around the x-axis, right? How will we compute that moment of inertia? And, well, here we go. Moment of inertia, integral r squared dm. Right, that, again, you should definitely memorize. Integral is a double integral because my domain is a two-dimensional region in the two-dimensional xy plane. Let's see here. dm, mass is density times size. Size in this case is area, again, because it's two-dimensional. The only thing we haven't made sense out of yet is what is r. So again, we're not going to have memorized cases. I'm just going to say, look, wherever you might happen to be looking, wherever you might happen to be in the xy in the region that we have here in the xy plane, if I want to know what is the distance to my axis of rotation, well, here it is. That distance, it's the y-coordinate. Right there in the picture, right? I don't need to have memorized it. I can see it. That is the definition of what y is. And so r is y. Is everybody all right with that? Does that make sense? Whatever the axis is going to be, this kind of analysis will answer the question for you. Okay. All right. So, last thing is just a quick pitch. You do have to make sure you're able to compute that integral. So make sure you're still good with your single variable integrals. Notice that one of the terms is integral of sine cubed times 2. So the challenging part of that integral is integrating sine cubed. And there's a clever little trick for that, right? And I know y'all certainly at some point in the past knew how to do that. Do you still remember how to do that? Well, okay, sadly, these integrals don't go away. Physics and engineering, you're going to be doing lots and lots of integrals, and single variable calculus is constantly a problem. The math department has gotten explicit and strongly felt requests from Pratt specifically. They have asked us to make sure that students continue to retain those Calc 2, anti-differentiation skills, because we need them to continue to be good at it. In fact, they were kind of complaining that students were coming out and kind of forgot how to do that stuff. Okay, so make sure you're good with that. If you have any questions about any of that stuff, always welcome, of course, to come talk to me. And now we are done with Chapter 5. We'll move along to Chapter 6. Excuse me. Okay, so y'all probably remember I talked a lot at various different moments in the past about how, and this is going to be super important in Chapter 6 and 7. Here we are, starting Chapter 6. A lot of exciting stuff that we're going to start thinking about. It'll really start to get good Wednesday, and then, of course, Friday is the exam. So the following lecture after that, Monday, there's going to be some wild stuff that we're going to start doing. We're going to see sort of a tip of the iceberg here, just a little bit. Notice every integral we've ever discussed, the domain has been the same dimension as the world that it lived in. So, for example, we've done a lot of double integrals on two-dimensional regions in a two-dimensional XY plane. And, of course, triple integrals over solid three-dimensional regions in a three-dimensional world. So what we're going to consider now is when our domains are dimensionally awkward, dimensionally kind of off. So for example, whoops, too far. What if we have a curve in the two-dimensional XY plane? So we have an intrinsically one-dimensional domain, right, over which I want to add some stuff up for whatever reason. But it's not a one-dimensional interval on the x-axis. It's a one-dimensional curve in a two-dimensional or even three-dimensional space. Right? We've never done this before. Okay, so how to do this? Well, let's maybe I'll mention some examples of why would we ever care about such a thing. So here's one that occurred to me. Well, let me start with here's a easier one to see. Let's suppose that this is a big thick cable, and I want to compute the mass of the cable that's lying around like this. And maybe for whatever reason the cable has to be thicker up here. Maybe it's because it has to be stronger up here because it has to be able to support more weight below it or something like that, right? So maybe it's thicker up here and thinner down here. How would I compute the total mass of that cable? Well, if you want to compute the total, you'd break it up into little small pieces. And on each little piece, I would think in terms of how much mass of cable per unit length of cable. Right? Does that make sense? And then I would add that up to get the whole. Now, technically, I suppose you could argue that the cable does have some actual thickness to it, and I could view that this isn't actually a one-dimensional curve domain. I could view it as being a three-dimensional solid and do a triple integral over a three-dimensional solid that's super-duper thin but long. What a weird domain that would be, right? That'd be a very unnatural way to think about it if you come down to it. How do we understand cables? What's the purpose of a cable? What do you do with a cable? You think of it in terms of length. Who cares how thick it is? We don't do anything with the thickness of the cable, right? We just need the cable to get from here to here. We think of length. We think about mass per unit length. Does that make sense? So it's just more natural to think of this as mass distributed over a one-dimensional curve, even if technically it's got a little thickness to it. Here's another example that occurred to me when I was, years ago, I was living in a house that was kind of semi out in the woods, and it a big piece of property, random circumstances. I lived out there for a year, and it had a driveway that was like, I forgot, let's say 250 feet long. It was a very long driveway. And it occurred to me, and thankfully this did not come to pass, but it occurred to me, oh my gosh, if it snows and I have to shovel that driveway 250 feet long, I'm gonna have to brag to my friends about how much work that was, right? I'm gonna have to compute how much snow there was on that driveway, right? So again, I could think of the driveway as being a super weird shaped two-dimensional, technically it does have some thickness, and I could think about that as a very, very strange shaped two-dimensional area. But it's a super weird two-dimensional area. It's much more natural to think about, okay, look, I'll just compute how much snow per unit length along the driveway, and then I could think of the driveway as being a curve. And it's just a much easier, much more natural way to do that. Does that make sense to everybody? All right. So, one-dimensional domain curving around in a two-dimensional world. We're going to break this up in a way that's very analogous to what we have done. We're going to think about little pieces of length. On each little piece of length, we're going to do a calculation where we multiply something times length. What do we multiply by length? I don't know. It depends on what we're trying to calculate, right? If you're trying to compute mass, if I want to know how much mass is on that little piece of length, I would multiply length times mass per unit length, right? Because mass per unit length times length would give me mass. That would tell me how much mass is in each little piece, and then I would add up over all the pieces, get the total amount of mass. If I, for what else, what if I were going to compute work, right? How much work does it take to shovel the snow? Well, I would need to multiply length times work per unit length. I would have to look at the particulars of the driveway and decide, okay, how much work per unit length does it take to shovel, let's say 1 foot of that driveway. And then again, add up over all of the pieces of the driveway. So this integrand, I think it's a great way to think about integrands. Integrands are always densities. Integrans are always quantity per unit size to be multiplied by whatever the corresponding notion of size is. Just like with every other integral we've ever seen. It's always stuff per unit size times size to give me stuff, and then we add up the stuff. Okay. All right. So this is called a line integral. Here's the notation that we use. You'll notice the notation is pretty strongly suggested by the little Riemann sum structure that we sort of wrote down there. And one clarification, this specifically is called a scalar line integral. Turns out there's another kind of a line integral that we're going to talk about soon. This is called a scalar line integral because the integrand is a scalar. And this is going to seem weird, right? We have seen very recently that there is such a thing as a vector integrand, and that we're kind of aware of. What we have not seen is that there will also eventually be a vector differential. And that's a creepy, weird thought, right? We haven't even begun to think about such a thing. But there is another kind of integral, we'll see it on Wednesday, where both the integrand and the differential will be vectors. We will then call that new construction a vector line integral, but we're not to that yet. This is called a scalar line integral. It looks like we're out of time, so we'll pick up here on Wednesday. See y'all later. Have a good one.